Hi, welcome to Math 4 Honors. I'm Kirk Weiler, and today we're going to be looking at derivatives involving exponential functions. This is one of my absolute favorite lessons of the year, especially the first exercise, because it's the first time in quite some time that we find the derivative of a function that's a little bit different. In my course, at least, all we really know right now is the power rule, the product rule, the quotient rule, and the chain rule. We don't know anything about trigonometric derivatives, logarithmic derivatives, exponential derivatives, or anything else. We can take the derivatives of polynomials, rational functions, functions that involve roots, but nothing else. So today we look at finding the derivative for the first time of sort of a different type of function. So let's take a look. In exercise 1, we're asked for the function f of x equals b to the x, determine df dx using the limit definition of the derivative. Now let me remind for you what that even looks like. Alright, I'm going to draw this exponential in an increasing manner. Okay, but of course the setup would work just fine if the exponential were one of the decreasing type. Whoops. Apparently this exponential function has a discontinuity in it. Alright, there we go. Now remember how this works, right? Newton said, I'm going to put a value of x here, and then I'm going to go a certain distance across. In my class, we've been using a lot of delta x. I'm going to go with saying that I go h units across this time, okay? Just so that you all see a different approach. Now, what I want to do is I want to calculate the slope of the secant line that connects those 2 points. But of course, I have to have a y-coordinate. Of course, at x, my y-coordinate is just b to the x. And at x plus h, my y-coordinate is b to the x plus h. So if I want the slope of that secant line, I simply say, well, that's b to the x plus h minus b to the x, all divided by my delta x, but that's h. Now I know in previous times I've used a delta x there and not an h, but both approaches are good. Keep in mind that h really is just delta x. Now if I want that secant line to become this tangent line, right, then what I do is I make this point move towards that point, and I do that by allowing my delta x to become 0. Alright, so I'm going to look at this as the limit as h goes to 0. Now the reason that I like this problem is, to me, this really illustrates one of the primary techniques in mathematics. I have no idea what to do. I actually do know what to do, but let's just say that you're doing this for the first time ever. You have no idea what to do. One of the things I want you to always give your permission to do, or give yourself permission, is to do whatever you want as long as you know it's not wrong. A lot of students think there's only one right way to solve a math problem, and that's completely incorrect. There might be a most efficient way and less efficient ways, but there are many different ways often to solve a problem. And sometimes we don't know what the complete correct path is. What we want to do, though, is make sure that we do things that are correct. So look at that numerator. What can we do? And let me give you a hint. How could you rewrite b to the x plus h as an equivalent expression? How would that look? Pause the video now if you need to think about it. Did you figure it out? What we don't want to do is we don't want to say it's b to the x plus b to the h, because it's definitely not. So that's what I mean by do anything you want, just make sure you don't do something incorrect. What I can say is that b to the x plus h is certainly the same as b to the x times b to the h, right? Whoops, I don't want an addition there, that's weird. Right, we know that exponent law. Now we're used to looking at the exponent law in sort of the opposite direction, i.e. if I asked you what b to the x times b to the h was, you'd probably tell me b to the x plus h. Alright, so again, let's take a look. I mean, I don't know if it's going to get me anywhere, but what I do know is it's not incorrect. So then I look at that numerator, and I ask myself again, well, is there anything I can do with that? Pause the video now and think to yourself, is there anything I can do with this numerator? Alright, let's take a look. Hopefully you said, I can factor out a b to the x. Right? And that leaves me with b to the h minus 1, all divided by h. Now, one property that limits have in general, alright, and this is something you've probably studied before. If I had the limit, let's say, of k times f of x, where k was some constant, I don't know, let x go to a, then I can actually factor that constant out. I can say, well, that constant really can just be brought out here, and then I'll just look at the limit of f of x as x goes to a, and then I'll multiply it by k. Now what's interesting in this problem is that x isn't the variable that's changing. It's h that's changing. As far as this problem is concerned, x is actually a constant, right? It's not moving at this point. So I'm going to factor that b to the x out of my entire limit. And this is what I'm going to be looking at. B to the x times the limit of b to the h minus 1 divided by h. Now, sometimes when math problems get long, you can kind of lose sight of what in the world you're even doing. Keep in mind what we're doing is we're trying to figure out what the derivative is, right, what f prime is as a function of x. Now, here's what's cool. This is the only place x shows up, right? So this is just some number. It's just some number. Now, it is a number. Let's call it L for limit, right? L for limit. It is some number that definitely depends on what the value b is, but it doesn't depend on what the value x is. X is not there. So this is really cool. Look at this. I'm gonna write it down in a box. First, let me just write out f of x. If f of x is equal to b to the x, then f prime of x is equal to some number, I'm going to call it L, times b to the x. That's really kind of cool. I'm going to actually write down cool. And the reason that it's cool is that it's unique, right? What we're saying is that if I've got some function, exponential, and I take its derivative, I get the same function, but just multiplied by some constant. That doesn't work with power functions, right? If I take something like x cubed and I take its derivative, I get 3 times x squared. I don't get 3 times x cubed, right? I get a totally different function here. But not here. Oh no, here, right? It says that if I have an exponential and take its derivative, I get the same exponential times some number. And granted, that number is not the same. That number is definitely dependent on what the base of the exponential is. So let's do a little exploration about what that number is, right? I mean, that's the real rub. I mean, I now know what the derivative of b to the x is. It's b to the x times something. But what is the something? So we're going to explore that a little bit. And I'm going to go back to sort of my delta x, but delta x, h, whatever. So I need to look at this limit. This limit as h goes to 0, delta x goes to 0. Doesn't really matter, whichever one you want. This could be b to the h minus 1, right? Look at that. You know, we're looking for this limit. All right. Now, I taught my students earlier this year how to evaluate limits using things on their calculator. So what we're going to do is we're going to experiment, granted, with some very strange numbers for the base. We're going to start off with a base of 2.4. So I really would like to look at this limit. You know, the limit, I'll show it with the h since I have the h up. You know, we want to figure out this limit. The limit of 2.4 to the h minus 1 over h. We want to figure out the limit of 2.6 to the h minus 1 over h, etc. So just as a review for my own students and other people that might be watching this video, let's take a look at how we do that in the calculator. So what I'm going to do is I'm going to go into my y equals, and granted, unfortunately, I'd love to be able to use h here, but I'm not going to. What I'm going to do is I'm going to use x, and I apologize for that. Remember, it's not really x, it's h. But what I want to do is I want to look at where 2.4 to the x minus 1 over x heads towards as x heads towards 0. So I'm going to go into my table. I'm going to make my table start at 0. And now I'm going to make it go by very small amounts. So maybe I'll make it go by 0.1 units. Let's go into the table and see what's going on. All right. No great surprise, like most interesting limits, what we see is that as we get very close, as we are at x equals 0, or h equals 0, we get an error. But coming from the two sides, I don't know. They look like they could be going to the same value. Let me go back into my table setup. Let me get a little bit closer. Let me have my table start at 0. Maybe have it go by 0.01. Right? Getting closer to 0 from both sides. Yeah, that looks pretty consistent. Now, if I look at it from the left, 0.87, from the right, 0.87 roughly, we could get it better and better. No need to. What we're going to do, we're just going to write in, I don't know, we'll write in 0.87. What I'd like you to do now, excuse me for that, is I'd like you to also evaluate the other two limits, the limit of 2.6 to the h minus 1 divided by h, and as h goes to 0, and likewise 2.8. This should be easy. You can go right into your calculator and change the 2.4 to a 2.6, then change the 2.6 to a 2.8. By the way, just to be clear, because I should have pointed this out before I went on to the 2.6 case, what this tells us, make sure that you understand this, is that if I were to ask you now, what is the derivative of 2.4 to the x, you would tell me that it is 0.87 times 2.4 to the x. Remember, we're not multiplying out 0.87 and 2.4 and then raising to the x. We're saying we've got 2.4 to the x that we then multiplied by 0.87. That is exactly what our result up here told us. Exactly what it told us, which was that our derivative will always be the original exponential function times this weird limit. So now let's get to why I chose these weird values like 2.4, 2.6, and 2.8. What I'd like you to do is pause your calculator right now, come up with these values by just going back into the y equals and changing the 2.4 to a 2.6 and a 2.8. See what you get. Alright, I'm not going to go through the calculator on both because I want to save us some time, but we get 0.96 and 1.03. Again, just to emphasize what this means is that if I took the derivative of 2.6 raised to the x, I would get 0.96 times 2.6 to the x. Likewise, if I took the derivative of 2.8 to the x, I'd get 1.03 times 2.8 to the x. So, I point out that these might seem like very, very strange choices. Why wouldn't I go with logical things like, I don't know, a base of 1/2 and a base of 2 and a base of 4, nice numbers? Well, if you notice, in each case, those limits that we came up with were numbers that were fairly close to 1, 0.87, 0.96, and 1.03. So, exercise number 3 asks us, from the table in exercise 2, does it appear that there's a base for which L is 1? Well, yeah, right? I mean, there's probably some number, right? Some number between these two where L is equal to 1, right? Somewhere. So I think I can say yes. Yes. Somewhere, between 2.6 and 2.8. And now here's the really cool thing. And I want you to think hard about this. I want you to pause the video and take some time. Why would finding a base where L is 1, why would that be significant? What would that exponential function have as a property that would be just cool? I mean, really, really kind of neat. Pause the video and think about that. Did you figure it out, right? What we know right now is that if we have y equals b to the x, then dy dx, or y prime, is going to be L times b to the x. But if L is equal to 1, then dy dx would just be b to the x again. So if I can find this magic number that gives me that limit to be 1, then I've found an exponential function whose derivative is itself. By the way, as a bonus, the second derivative would also be itself, and the third derivative would also be itself. That's just amazing. And yet that number exists, right? It's some number between 2.6 and 2.8. So we come along and we just give it a name. We say, well, maybe I don't know its exact value, but I'm going to call it E. At least I'm going to call it E if I'm Leonard Euler. And that's our winning number. All right, and this is amazing, right? There are, in my mind, and there's probably professional mathematicians that would disagree with me on this in a huge way, so I apologize, you guys, if you're watching this, or ladies. If there are very few functions that are their own derivatives. In fact, probably the only other one I can really think of off the top of my head without getting fancy is y equals 0. Clearly, y prime is also equal to 0, etc. But that's what we would call a trivial case in math. This is amazing. Y equals e to the x has as its derivative itself. Isn't that kind of cool? It actually means that the y-coordinate on the slope function is the same as the y-coordinate on the normal function, or better yet, the y-coordinate on the normal function gives you the slope on the normal function. I don't know why I keep calling it normal. So, of course, using that fact, what we want to do now is we want to find derivatives that involve e to the x. So let's take a look at some of these. We'll start off very simple. In the first problem, letter A, we want to figure out what the derivative of e to the 2x is. Now, I want to really make sure you get this correct and you understand the thinking behind it, because this will serve as the basis for most of the rest of the problems involving e, with the exception of letter D. All right? So, what derivative rule do we use? Well, we use a derivative pattern, and that's going to be this. But there's an additional rule here. Pause the video and see if you can think about what the additional rule is that we'll have to bring in one of the big four to take the derivative of that. Pause now. Alright, I'm kind of hoping you realize that you have to use the chain rule. Now, let me explain why. If I asked you to write this as the composition of two functions, right, it would be. Right? This really is an f of g of x kind of scenario, right? The inner function is 2x. The outer function, if you will, is e to the x. So remember how the chain rule works, right? It says take the derivative of the outer function. Whoops. Definitely want to write down the rule correctly. While leaving the inner function alone, and then multiply it by the derivative of the inner function. The thing that's hard for people here is that they don't normally see this as sort of an inner function. But that's the way I want to think about it. I literally want to block out the 2x. I want to say e to the whatever is the sort of outer function. So I cover up the whatever, I cover up the 2x, and I say, what's the derivative of e to the whatever? The derivative of e to the whatever is e to the whatever. Boy, this is really starting to devolve a little bit, right? But then I have to multiply it by the derivative of the inner function, which is just 2. So I get 2e to the 2x. And I really want you to understand that that's the chain rule. Because I get some people, I think, who look at some of these problems and they kind of get into the swing of things and they think about them and they think about them. And they start to believe that this is some type of a power law, as if I'm like bringing the 2x power down and multiplying by it. And in fact, I'll oftentimes see students make that mistake. They'll say, oh, its derivative is 2x to the e to the 2x. And it's like, oh, no, sorry, that's just not what it's equal to. Right? This is pure chain rule. And so is problem B. So pause the video for a second and see if you can extend what we did in problem A to do problem B. Alright, let's do it. So again, we do have two functions. The outer function, if you will, is the e raised to the whatever function, and the inner function is the negative x. You're going to take the derivative of this function a lot, so it's really a good one to get down, right? So I ignore the inner x. I say, well, what's the derivative of e to something? And that's going to be e to the something. Then I have to multiply it by the derivative of something, but the derivative of e to the x is negative 1. Most of the time, we'll just write this as negative e to the negative x. All right, take a look at letter C. Y equals x times e to the x squared. We need to find its derivative. Pause the video for a moment and think about what major derivative law you would use to find this derivative. All right, hopefully you said the product rule. I'm hoping, right? Because that's what we have. We have the product of x times e to the x squared. So remember the product rule, right? If I have f times g and I'm finding its derivative, I take the derivative of x, I multiply it by g, then I add to it the derivative of g multiplied by f. So here we go. Let's find dy dx. All right. We're going to take the derivative of the first quantity. We're going to get 1. We're going to multiply it by the second quantity, e to the x squared. So check, check, plus. Now I have to take the derivative of e to the x squared. All right, this is where the chain rule will come in again, right? We've got an inner function, which is x squared. We've got an outer function, which is the e function. So I cover up the x squared, and I say, what is the derivative of e to the whatever? And that's e to the whatever. Then I multiply it by the derivative of the whatever, which is 2x. Now keep your eye on the ball, folks. All we just did was find g prime. We still need to multiply it by f, right? So we still have to multiply it by that extra x. We can clean this up a little bit. I'd rewrite it as e to the x squared plus 2x squared e to the x squared. Awesome. Let's take a look at letter D. Pause the video again, ask yourself, what derivative rule am I going to use? If you're confident that you know what rule you're going to use and how to use it, work through the entire problem. If not, wait for a moment. Alright, did you figure out you had to use the quotient rule? Alright, if you didn't, that's the rule you're going to use, because we definitely have a division here. Pause the video again and see if you can figure out what the answer is with the quotient rule. Okay, let's go through this. Now I'm going to go through the entire thing, including the simplification process, because something kind of quirky happens here. Just a little review of the quotient rule. If I have f divided by g, and I find its derivative, I'll find the derivative of the top times the bottom, minus the derivative of the bottom times the top, all divided by the denominator squared. Alright, so let's do it. Give myself a little line here so that it doesn't get confused with the last problem. dy dx. Alright, the derivative of the numerator. Well, you don't get any easier than that. It's e to the x times e to the x plus 1. Check, check. Minus, check. Alright, the derivative of the denominator. Be careful here. That's just going to be e to the x, right? Because the derivative of e to the x is e to the x, and the derivative of 1 is 0. And then I have to multiply it by the numerator. Oh, got that. That's e to the x. Check, check. And then, of course, I don't want to forget to square my denominator. Now, be careful, folks. Of course, it's always visually tempting to think that you should cancel this and this, but remember, only cancel after you've done things like factoring, and that numerator is definitely not factored. Now, a lot of people actually would make a mistake if they tried to simplify the numerator. Some people wouldn't make a mistake, but they would actually get some people would make a mistake and actually get the right answer. Here's what I'd like you to do. Take a moment if you haven't simplified this and take a shot at simplifying it. But then make sure to watch me simplify it. Okay, let's do it. So to simplify this, we're going to obviously distribute the e to the x. Now here's the key. What is e to the x times e to the x? A lot of people want to tell me that it's e to the x squared, and it's most certainly not. E to the x times e to the x, well, we add the exponents when we multiply two things of the same base, so we get e to the 2x. Then, of course, when we do e to the x times 1, we just get e to the x. That's simple. And then we get minus e to the 2x. We're not going to square out that denominator, almost ever. Alright, but now we can cancel these two terms, and we're going to be left with e to the x divided by e to the x plus 1 quantity squared. Alright, getting a little bit of bleed through on the noise. But then again, it's my principal, so I don't think I'm going to go tell him to be quiet. That would probably get me in trouble, obviously. Let me pause the video for a second, and maybe we'll wait it out, although I doubt you can hear it all that well. Alright, we're back at it. You know, I've always kind of wondered what it would be like to freeze time, and every time I hit pause in these videos, it gives me the sense that I can. You know, while I had paused the video, I had a cup of coffee, the hallways got quiet, it was great. Anyway, we're back to it. So, really, from now on in this course, and you should really have this mentality if you ever take a calculus course, once you know the major derivative rules, and you know the major applications of derivatives, like finding local maximums, minimums, concavity, inflection points, things like that, then every new function that gets introduced, it's going to be just a pattern. The derivative of e to the x is e to the x. In the follow-up lesson to this, we'll figure out what the derivative of the natural log is, and you'll have to memorize that. But you should take every advantage of these kind of scenarios to try to then refresh in your mind the techniques of calculus. So Exercise number 5 gets at that. It asks us to find the classify. Well, there's a little bit of a typo. Whoops. This should really say find and classify the local extrema of the function f of x equals x to the third times e to the 2x. So we want to locate them, we want to find their x-coordinates, and we want to figure out whether they're maximums or minimums, right? We want to find these things, these guys. All right, so if you remember, what we do in that case is we're going to figure out where the tangent lines are horizontal, and we're going to do that by setting f prime of x equal to 0. Take a moment, pause the video, and try to figure out what f prime of x is. Alright, let's make sure everybody's on the same page before we do the algebra. Alright, we're going to have to use the product rule to find f prime of x. We're going to take the derivative of x to the third. We're going to get 3x squared times the second function, e to the 2x. Then we're going to add to it the derivative of e to the 2x. This is going to be chain rule, and often will be chain rule when we have e raised to something other than the x, right? So the derivative of e to the 2x would be e to the 2x times 2. Remember, that's just the chain rule, but we can't forget to then multiply it by the x cubed. Very often when you have a mixture of sort of power functions like these two and exponentials, the power function tends to be written first. Give me just a second, I'm going to pause the video. Alright, after a little conference with the teacher, let's get back to the algebra on this particular problem. Where'd my pen go? There it is. Alright, so as I was saying, if you've got some mixed up exponentials and power functions, I find that it's always kind of an advantage to sort of bring those power functions, if you will, in front of the exponentials. Alright, so here's our final derivative. Right? We want to figure out where we have local extreme values, so we're going to set it equal to 0. Now, if you haven't had a chance yet to try to solve this equation, what I'd like you to do is spend a little bit of time now and see if you can solve this equation set equal to 0. Meanwhile, I'm going to erase this terrible looking 3 and make it look a little bit less terrible. Anyway, why don't you pause the video and try to solve for that and see where you come. Alright, let's take a look at the algebraic solution for where we have horizontal tangent lines. I'm going to be biased towards the zero product law. First thing I think I'll probably see is that there's a GCF, well not a GCF, but a CF, common factor of e to the 2x. So when I factor that out, I'll have a 3x squared and a 2x cubed. I might want to go a little bit farther and pull an x squared out, so I'll have x squared times e to the 2x times 3 plus 2x. Is that right? Think a little bit about it. If I distributed the x squared back in, I'd have that. Yep. So now the zero product law is very clear to me. Either this is true, or this is true, or this is true. I'm going to end up running out of room. I can't believe this. Alright, well, this is easy enough, right? We get x equals 0. This is also quite easy. We get x equals negative 3/2. And how about this? What do you get as a solution to that? Pause the video right now if you haven't thought about it. Alright, let's talk about it. I'm really hoping you told me that that has no solutions. Alright, now, we need to classify these things. So what we're going to do is we're going to draw a number line of the first derivative. I might eventually erase some of this work, and I apologize for that, but do a number line analysis of the first derivative. I'm going to put my 2 critical points on there. Oh. No. How about this? How about negative 3/2 here and 0 here? And then I'm going to test the signs of my first derivative in this factored form of the derivative, right? There's my f prime, all factored. Why don't you pause the video now if you haven't done a sign analysis yet? Alright, if we actually do the sign analysis, and I've really just worked with these time and time again in my class, what you'll find is you'll find this. No great surprise, we find no sign change across x equals 0 because it is a repeated root. That means we do not have a max or a min there, but we do have a minimum there. Let me just erase some of this. The beauty of electronics. Alright, so we would finally say x equals negative 3/2 is the location of a relative minimum, right? Because, remember, always cite information about the first or second derivative, because f prime of x changes. How does it change? At a min, it changes from negative to positive. Alright, well, a lot of interruptions there, but we got through it. Let's take a look at number 6. Number 6 asks us, is the function f of x, which is equal to e to the negative x minus x squared, concave up or concave down at x equals 1? We want to do this without our calculator. Alright, so what I want you to do is pause the video right now, especially if you have to go back and think or review what you know about concavity, right? What do we know about concavity? So, pause the video now if you need to. Alright, hopefully what you remember is that concavity is all about the sine of the second derivative, right? We're concave up if the second derivative is positive, we're concave down if the second derivative is negative. So, all we need to know is whether f double prime of 1 is positive or negative. So first thing we have to do is find f double prime of x. Please go ahead and do that now. Pause the video. Take as much time as you need. Alright, let's figure out what f double prime is. Of course, we have to figure out f prime of x first. We need to find the derivative of e to the negative x. We already did that once. We got it up above. It's negative e to the negative x. Of course, we have to also take the derivative of x squared, and it's negative 2x. Taking the derivative again, what we would find, right, is that we would pull that negative 1 kind of out to the side. We'd take the derivative of e to the negative x again, which would introduce another negative. Of course, this would just give me negative 2. And I'll find that the second derivative is a positive e to the negative x minus 2. So I need to figure out what f double prime of 1 is. So that's going to be e to the negative 1 minus 2. Now, one thing that's interesting is I gave you the piece of instruction to do this without your calculator. This could show up on an AP exam or in a non-calculator college calculus course. So we have to be able to figure out whether or not this is positive or negative. And that might be a little bit tricky given the nature of e. So always keep in mind, if you're just trying to figure out whether this would be greater than 0 or less than 0, that e is approximately 3. I know a lot of people would probably yell at me for that, but ironically they wouldn't yell at me if I said that e was about 2.7, right? So the nearest integer, e, is about 3. So if I want to think about what this is, right, 1 divided by e minus 2 is approximately 1/3 minus 2, which is definitely less than 0. And because the second derivative is less than 0, we can now say that the graph is concave down. Of course, remember, if I know a graph's concave down, I can also say that the tangent line lies above it. The question didn't ask that, but who knows, maybe it'll show up on homework. Alright, thank you again for joining me. I'm Kirk Weiler. This has been Math 4 Honors. Until next time, keep thinking and keep solving problems.